Okay, so since so many of you guys were absent this week because of being sick or sports or family trips, I'm going to do a video of our day one of the 2.1 limit section, and then I'll do a separate video for day two. So in section 2.1, you're learning about the 3 different methods for evaluating limits. So we can do that numerically, graphically, or analytically using algebra. And we're going to first focus, in this first video, we're going to focus on evaluating limits numerically by creating a table of values and graphically by analyzing the graph of the function that we're taking the limit of. So the idea behind a limit is thinking what happens to the values f of x of a function f as x approaches the real number a. So basically, as x approaches some number, what's happening to the y values? Are the y values approaching a number? Are they approaching infinity, negative infinity? What's happening to the y values as x approaches some number? Okay, here's kind of our intuitive definition of a limit. It's not the formal definition of a limit. We're not going to worry about the formal definition in this class. But it says that if the values of f of x become arbitrarily close to L as x gets sufficiently close to a but not equal to a, then all 3 of these statements are equivalent. So the limit of f of x as x approaches a is L. This reads the limit of f of x as x approaches a is equal to L. And then I showed you guys this last week where the arrows mean approaching. So f of x approaches L, which L is just a number, as x approaches a. And again, a is just a number. So we're going to consider these 3 cases where the limit exists. So where this is a true statement. So our first case, draw my graph, is where if we have a function, some general function, I'm going to name that function f, like the function that's having the limit taken. Okay, and let's say x equal to a is right here, okay, where the y value that corresponds to a is L. So the function evaluated at a is equal to L, and that matches the limit of the function as x approaches a being equal to L. Okay, so that's our first case. Our second case where this is a true statement I'm going to try and draw a similar curve. Would be if this is x equal to a, okay, this is going to be L. Okay, so this second case says that the function evaluated at a is not equal to L. It's actually equal to some other value. So whatever this y value is here, the function is actually equal to when evaluated at x equals to a. So I can say f of a does not equal to L. This could happen if we have like a piecewise function. So that's our second case. And our last case would be if there's a hole at x equals to a. That was my function f. Okay, where the function evaluated at A is actually undefined. The limit of the function as x approaches A is still equal to L, but f of A, that's fine, is undefined. So there's a hole. Okay, so that's our third case. This can happen with like a rational function. It could happen with a piecewise function too, but it could happen with a rational function where we have a common factor in the numerator and denominator that would cancel, causing a hole. Okay, so we're going to keep coming back to these cases. We're going to look at more specific examples where we take limits of functions as x approaches A and the limit exists. And we're going to come back to this diagram to look at which case we're actually looking at. Okay, so we're going to start by estimating limits numerically and graphically. We're actually evaluating the limits, but I like to say estimating, especially whenever we're creating a table of values to determine what the limit is. Okay, so we're going to be using our calculators a lot. So we're going to fill in our table of values, and we're going to sketch what the graph looks like so that we can look at both to determine what this limit is. So the first thing that I want you to do is to graph y equals to negative x minus 3 squared plus 2 in your calculator. I'll do it 2. This will make it easier for us to fill in our table values as well. And you can just do z standard for your window. You can kind of see it in here. All right, so it's a parabola that's opening down. The parent function is x squared, and x squared has a vertical reflection, is being shifted to the right 3 units and up 2. So my vertex is going to be at 3, 2. And then I know those other points that have been shifted. Okay. And okay, so here is the sketch. Of our function. Label some of our x and y values. Okay, so looking at our graph, we're thinking as x becomes closer and closer and closer to 2 from the left and the right hand side, so here's 2. So as x gets closer and closer and closer to 2, what are the y values approaching? And it looks like the y values are approaching 1. And we can confirm that by creating our table. So to fill in our table, instead of having to substitute each of these numbers in or use my calculator to substitute each of those in and type it in every single time, I can just hit trace and I type in 1.9, enter. Okay, and I can see the y value is 0.79. Okay, 1.99. Okay, when I type 2 in, I get y is equal to 1. And 2.1. Okay, so looking at the table, we can see that as the x values are approaching 2 from the left of 2, remember, we don't care what's actually happening at x equals to 2. So as x approaches 2 from the left-hand side, it looks like the y values, or the values of f of x, are approaching 1. As x approaches 2 from the right-hand side, it looks like the y values are getting smaller and approaching 1 as well. Okay, so therefore we can say the limit as x approaches 2 of our function is equal to 1. As our x values approached 2, our y values were approaching 1. All right, our next example, let's start by graphing again in our graphing calculator. Oh my goodness, it looks like a line. Why could that be? So looking at the equation for your function, it's a rational function, and we see that the numerator can factor 2x minus 1 times x plus 1, where our x minus 1 factors will cancel. We're left with x plus 1. So there's actually a whole at x equals to 1, right? Think back to pre-calc. So the graph of this function looks like the graph of x plus 1. So that's a line with a y-intercept of 1 and a slope of positive 1. But there's going to be a whole, or the function will be undefined at x equals to 1. So let's go ahead and fill in the table. So if we again use the trace, oh, well, that makes sense. And let's look then what happens whenever we type in 1. Oh, y is undefined because of that hole. Okay, and let's sketch the graph. Like I said, it's a line with a y-intercept of 1. There is a hole at x equals to 1. Okay, so we think, what is happening to our y values as x is approaching positive 1 from both sides? So looking at the table, it appears that our y values on each side are approaching positive 2. Remember, for limits, we don't care what actually happens at this x value. We just care what happens in the neighborhood of the x value. So as we get really close to x equals to 1 on the left, we can see our values are approaching 2. And as x gets really close to 1 on the right-hand side, we can see that our y values are also approaching 2. So we're able to say that the limit as x approaches 1 of x squared minus 1 over x minus 1 is equal to 2. Okay. Oh, going back to our chart. So the first example that we looked at, that was an example of the first case of when the limit exists. Okay, so this is a polynomial function, it's a smooth continuous function, so the limit 1 matches what the function evaluated at x equal to 2 is. This example is our third case of whenever the limit exists. So we actually had a hole at x equals to 1, but our limit was still a finite value, so it's still 2. Okay, so for this one, make sure that you are in radians mode when we go to graph. So we're going to first graph y equals to sine of x over x. Make sure your calculator is in radian mode. Mine already is. Go to your y equals sine of x divided by x. Now to see a good, to see this graph, I'm going to adjust the window. So I'm going to make my x min negative 2 pi, my x max 2 pi, my x scale pi over 4. I'm going to try negative 3 for my y min and 3 for my y max and leave the y scale as 1. Okay, so it kind of looks like a sine curve except for the waves are not even. They're smaller to the left and right of the origin. All right, so let's fill in our table first. So using trace, okay, negative 0.001. How many nines is that? 6 nines. Now that's not true. The trace is just not that smart. Oh. So I'm going to go out of my graph and type in sine of negative 0.0001 divided by negative 0.0001. So what is that? 1, 2, 3, 4, 5, 6, 7, 8 nines. 1, 2, 3, 4. Okay. Now going back to my graph and trace. If I type in 0, I see y is undefined, and that makes sense, right? Since we have an x in the denominator here. If we substitute 0 in, we would end up with 0 inside the denominator. Okay, 0.0001. Oh, the trace is wrong. So we can see on the graph that it's symmetric about the y-axis, so I can actually just fill in the table, the rest of the table using these other values. Okay, and let's go ahead and sketch the graph. So I'm going to say this is 1. There's a hole at x equals to 0. The graph kind of comes down. This is just a rough sketch. Okay, so as x is approaching 0 from the left-hand side, it looks like those y values are getting closer and closer and closer to 1. Our trace, even when we typed in negative 0.0001, gave us 1 because it's so close to 1. And then also from the right-hand side, as x approaches 0, our y values are also approaching 1. So we can say that the limit as x approaches 0 of sine of x over x is equal to 1. And we see this on the graph as well. This is also this third case where the limit exists, where we have a hole at x equals to 0. A is equal to 0 for this one. Okay, now those were all examples of where the limits exist, but sometimes the limits fail to exist, okay? Some examples of when that can happen are if we have piecewise defined functions that have a jump in their graphs, functions that have increasingly oscillating behavior, like sine has oscillating behavior where the y values bounce back and forth between -1 and 1. But we're talking increasingly oscillating, and I have a specific example to show you. And then functions with unbounded behavior, like if we have a vertical asymptote and we're asked to take the limit as x approaches whatever that value for the vertical asymptote is. So we'll look at some specific examples now where the limits fail to exist. Okay, piecewise function. You guys know how to graph piecewise functions. So let's go ahead and sketch this graph first. So for x strictly less than 2, the graph will look like y equals 2x. I'm putting an open circle at x equals to 2 since it's for x strictly less than 2. And then for x greater than or equal to 2, the graph will look like x squared. Oh, and if you want to graph this on the graphing calculator, you can write it in or type it in as y equals, and then in parentheses x less than 2 plus in parentheses x squared in parentheses x greater than or equal to 2. And I'll type that into the calculator so we can use the trace. Okay. X parentheses x, to get the less than or equal, the strictly less than symbol, I'm going second math, where you see it says test over it. I'm going to adjust my zoom to Z standard. Okay, so we can see our graphs look pretty similar. Okay, so filling in the table, when x is less than 2, so to the left of 2, if I substitute these values in, they're going into the y equals to x. The identity function, so just 1.5, 1.9, 1.99. Now, when x is equal to 2, that's this interval, so I'm going to square 2 and I'll get 4, okay? And then 2.01, so if I hit trace and type in 2.01, I get 4.0401, and then if I type in 2.1, I get 4.41. If I type in 2.5, I get 6.25. Okay, so let's look at this. Let's look at as x approaches 2 from the left-hand side first. So as x approaches 2 from the left, f of x, so our y values seem to be approaching as x approaches 2, and I'll show you notation in a little bit or in the next video for so we don't have to write out from the left or from the right. So as x approaches 2 from the right, our y values look like they're approaching, so as x approaches 2 from the right, our y values look like they're approaching 4. So, as we get in the neighborhood of 2, x equal to 2, our y values are actually approaching 2 different numbers. So that means that the limit is going to have to fail to exist because our y values are not approaching the same number. So we would say the limit as x approaches 2 of f of x dne does not exist. Okay. So for this next one, again, we're already in radians. So we can go ahead and graph sine of pi over x. And it says for the window to do -1 to 1 and -1.5 to 1.5. Okay, so this is an example of a function that's becoming increasingly oscillating. And what that means is as x approaches 0 from both sides, the function starts going back and forth super, super fast. So as x equals to 0, it's really hard to see what our y values are actually approaching. So let's fill in these two tables and look at what happens. So using the trace, if I type in -1, I get 0. -0.1, oops, 0. 0. Undefined. Zero. 0. 0. Okay? But now if I fill in this table where I have x values that are also in the neighborhood of 0 and approaching, oops, that's a D. Okay, so if I type in -2/3, I get y is equal to 1. -1, 1, -1, 1, -1, 1, -1. Okay, so look at what's happening. So in this first table, and this is why I also like to say that tables we're estimating the limit, because look at these two tables, look at the values that we have in them. In this table we can see that our y values are oscillating sure I'm spelling oscillating right. Yeah. Oscillating between -1 and 1. So that means that as x approaches 0, we're not going to know whether or not y is approaching 1 or -1 or some value in between there. So we have to say that the limit dne does not exist. Okay. So 1 over x squared. First thing, go ahead and graph. This is the last example for this first video. Okay, so if we graph 1 over x squared, changing my zoom back to z standard, okay, so I have the two branches. Now, there's a vertical asymptote at x equals to 0, and a horizontal asymptote at y equals to 0. Remember from us studying rational functions in the past, if the denominator has a larger degree than the numerator, then we're going to have a horizontal asymptote at 0, because as x gets really large, our y values will approach 0, and as x gets really small, our y values will also approach 0. So we'll have points 1, 1. And negative 1, 1. Okay, so let's go ahead and fill in the table first. Whoops. So using trace, oops. So look at what's happening. You get 1 million. Okay, so looking at the table, as x gets closer and closer to 0 from the left-hand side and the right-hand side, our y values are getting larger and larger and larger. Now on the table, we can't necessarily tell whether or not they're going to continue to increase without bound. But on the graph, we definitely can. So we can see on the graph, as x gets closer and closer and closer to 0 from the left and the right-hand sides, our y values are increasing without bound towards positive infinity. Now because positive infinity is not a finite value, the limit technically fails to exist. However, to describe the behavior of the function, we say that the limit as x approaches 0 of 1 over x squared is equal to positive infinity. Okay, so I am going to save one-sided limits and the rest of 2.1 for the next video.